Alright, hello class. In this video we're going to be talking about Green's theorem, and Green's theorem connects a lot of the ideas that we've done in this class completely. And I mean, on the shorthand, it's connecting divergence to flux and curl to circulation. But it's also connecting things like line integrals to multiple integration. Let's take a look at what Green's theorem says and get down into it. All right, now before we really get into what Green's theorem says, we need to talk a little bit about the types of paths and curves and types of regions that they can enclose. So let's talk about the types of paths that we can have. There is closed, okay, which we've talked about. That's where we start at the same point and where we end, right? But we can have other forms of closed paths too, like the figure 8, right? We're still starting and ending at the same place, but we're sort of crossing over ourselves and having, an intersection point, right? Okay, now, so that's closed. These are both closed paths. A simple path, okay, doesn't cross over itself. Okay, so this path here, this would be simple and closed. Okay, this path here would just be simple but not closed. Okay, here this is closed and not simple. Okay, and then if we made this path something like this, this would be not simple and not closed. Okay, so if something is simple and closed, it looks like this. And simple and closed basically is, you could say, equivalent to a circle, right? Because even if it's not shaped like a circle, it could probably be manipulated into a circle. Like if it's a rubber band, you could stretch it out to be a circle. So it's either a circle or something that could be transformed into a circle easily, right? So I kind of think of these as generic circles or general circles if they are simple and closed. All right, now let's talk about the types of regions that we're going to be considering when we're talking about Green's theorem. The first is connected. Okay, so a connected region, it's basically if it's possible to join any 2 points in the region by a continuous curve. Okay, so basically if our region R, say this is our region R, it looks like this. This would be connected because any 2 points can be connected by a continuous curve. And we can do that with any 2 points we choose in R. We can easily connect them. Right? So this would be connected. A region that wouldn't be connected would be something like this. Suppose S is this little bit here and then maybe a bit over here. Right? So these together would be S. And this is not connected because if I have a point in this region and a point in this region, there's no way I can get over to it completely in S. Okay, so that's what we mean by can we connect any 2 points without leaving the region. That's that. Okay, now this one, the next topic is a little more complicated. This is simply connected. Simply connected basically means that there's no holes in the region. Okay, so it's easier to show something that's not simply connected. So something like this. The donut shape or the disc shape. This is not simply connected. Okay, it is connected. Okay, but it's not simply connected because, well, between any two connected points, right, we can make like a continuous path that would connect them, but there's a hole. Okay, so basically, simply connected means no holes in the region. Mathematically, rigorously, there's way more to it than that. I don't want to get deep into the woods here. Basically, there should be no holes in R. Okay, so no holes in our region. Okay, now these guys you could say are simply connected because where they are connected there are no holes. However, they're not connected. So these individual pieces are simply connected, but the whole thing is not connected. Okay, so the reason that we need this is because in Green's theorem, okay, what Green's theorem requires is basically a path that is counterclockwise, okay, closed and simple. Okay, and we need that path C to enclose a region R, and that region R needs to be connected and simply connected. So in other words, the curve itself shouldn't cross over itself, and it needs to be closed, counterclockwise, and the region in it, it can't have any holes in it, and if it should be it should be connected if it's enclosed within a closed simple curve, but we just need all this to happen, and specifically it's about how we need the vector field to behave over the region that we're enclosing. Okay, so now that we've gotten this out of the way, let's talk about what Green's theorem actually says. Okay, so to start Green's theorem, we let C be a simple, closed, piecewise smooth curve oriented counterclockwise that encloses a region R that is connected and simply connected. So in other words, we might have a curve that looks like this, oriented counterclockwise, enclosing a region R that has no holes. Okay, now what the piecewise smooth means is that we could do this over a square, right? Because while it's not completely smooth, each individual piece is smooth. Okay? All right, so if that's true, and if F is the vector field little fg, right, it's a vector field where f and g have continuous first partial derivatives in the region R, so that's why we shouldn't have any holes, because if there's a hole there, what we're saying is that f isn't, say, continuous completely inside of the path C. I didn't label these here. See? Okay? So if all this is true, then we have the following. Okay, so here's the circulation form. So if all this is true, then the circulation, or the integral over C of f dot dr, okay, now, when Green's theorem is being invoked, it has its own integral sign with this little circle. I'll talk about in a minute what I mean by that, but basically this means that C satisfies all those things. It's counterclockwise, it's piecewise smooth, it's oriented counterclockwise. Or I think I said that already. Oh, and it's simple. Okay, so the circulation can instead be calculated as the double integral over R, okay, of the curl of f, which in other words is the, dA, which in other words is the double integral over r of g sub x minus f sub y dA. Okay, and then there's a flux version of this. Okay, so the flux version of it is the line integral over c of f dot n ds will be instead the double integral over r of the divergence of f dA, or the double integral over r of f sub x plus g sub y dA. Okay? So, what we're basically saying is that the circulation, okay, which is this line integral, is the same thing as the double integral of the curl of f over r. Or the flux, which is this line integral over c, is the same thing as the double integral of the divergence of f. This is actually a really fascinating property. I think so anyway. Let's take a look at a little picture to kind of show what we're talking about. Okay, so if we have a vector field and we're looking at a curve C and a region R enclosed by it, what Green's theorem is saying is that the circulation over this line integral is going to be the same thing as basically calculating the double integral of the curl. Well, let's think about that. Let me set this up so that we have a positive circulation. Right? So positive circulation would be that the vector field F goes along with the path over the whole life. Right? That's one way to do it. Right? And what the curl does, well, if we have a positive curl, that means all the points want to rotate counterclockwise. Right? So positive circulation from the line integral over C of f dr. And this is all positive curls at every point in R. Okay, so what Green's theorem actually says, and I think it's really fascinating, is all right, so the circulation measures how much of the field actually goes with our path as we travel. The curl is the tendency for points within the vector field to rotate. So you can think of all of these little guys in here rotating, and if they're all rotating, you could expect that the path along here, right, that the vector field will be rotating around this region in the same way that all these little points are rotating. I think this is really fascinating. Okay, and we have a similar idea for the flux, right? If we have a curve C and a region R enclosed within, and let's say we have a positive flux, so maybe we come in this way and we exit this way so that we get, say, a positive flux. Okay, which will be the line integral of f dot n ds over rc. What Green's theorem says is what we can basically do is just calculate the divergence of the entire region. And the way that the divergence is behaving within the region can tell us how the flux operates on the boundary. All right, so essentially Green's theorem tells us that the circulation on the boundary of our region R, which is our path C, is completely determined by the curl within R. Similarly, equivalently, the flux on the boundary of R, which is our path C, is completely determined by the divergence within R. Okay, so these two things are joined together, and what Green's theorem tells us is how they are joined together. Specifically, that the circulation is the double integral of the curl, while the flux is the same thing as the double integral of the divergence. Okay, so let's take a look at some examples and show how nice Green's theorem is for us, because it may seem kind of complex, it may not seem that useful, but in practice it can be extremely useful. Okay, so for example, let's find the flux of capital F, which is equal to y minus x, comma x over c, which is the circle, or c is the circle oriented counterclockwise, centered at the origin with radius 2. For the remainder of this class, one, should probably learn how to spell oriented, but two, this part of the circle, I want that to be a given, okay? That oriented counterclockwise, centered at the origin, we can assume this is a given unless told otherwise. Right, because typically for most of what we're doing, we're centering our circles at the origin, we're orienting them counterclockwise. That happens pretty much all the time. It's more probably efficient if we just say when we're not doing this. So if we center it somewhere else, we'll say that. If we're orienting it in some other direction, like clockwise, we'll mention that. That usually doesn't happen, but we can change the center and we'll say that instead. But if we're not saying it, we're just going to assume that's the way it goes, okay? So, all right, so if we were to do this the normal way, right, we'd actually have quite a process in front of us, right? Because first we need to find f of r. Well, first we need r, right, which will be the 2 cosine t, 2 sine t. Then we would need f of r, which would be the vector 2 sine t minus 2 cosine t, comma 2 cosine t. All right, then we would need r prime. So negative 2 sine t, 2 cosine t. Then we would need our actual n, where we flip this around as 2 cosine t, 2 sine t, because remember our little n is y prime comma negative x prime. Then we need to take the dot product, which is f of r, dotted with our n. So in this case, that will be 4 cosine t sine t minus 4 cosine squared t, then plus 4 cosine t sine t. All right, so we'll have 8 cosine t sine t minus 4 cosine squared t. And then we would need to integrate this from 0 to 2 pi, because that will be our t values for the full circle. Okay, now this isn't impossible. It's maybe not even that difficult if we use identities, because we can use the fact that sine of 2t is 2 cosine t sine t to get that this is 4 sine of 2t. And we can use the half angle formula to get that this is minus 2 cosine of 2t. All right, so the flux will be the integral over c f dot n ds, which will be the integral from 0 to 2 pi of 4 sine of 2t minus 2 minus 2 cosine of 2t dt. Okay, so from here then, we'll just integrate, and this will get negative 2 cosine of 2t minus 2t minus sine of 2t. I'm kind of speeding through this, but hopefully we've done this enough by now that this isn't too shocking. These guys are going to go to 0 because plugging in 0 and 2 pi will be the same thing, so then when we subtract them, they'll cancel and become 0, and so we'll get negative 4 pi when it's all said and done. Okay, so there's our flux. This field is wanting to, well, along our path is, so there's more, say, leaving than entering if we're looking at the path here. Okay, now, like I said, this isn't impossible. This isn't that terrible. However, let's look at what happens if we use Green's theorem. Okay, so by Green's theorem, the line integral, or the flux integral, I'll just say, f dot n ds will be equal to the double integral over r of the divergence of f dA. Well, the divergence of f in this case is actually going to be quite simple because it's, remember, little f sub x plus little g sub y dA. Well, little f sub x will be negative 1, right? And then g sub y will be 0. So we're just taking the double integral over r of negative 1 dA. Not a very complicated integral. Now our r, we do need to think about that. Well, our path is this circle, right, of radius 2. Okay, and provided we set this up in polar coordinates, this integral won't be that difficult to calculate, right? Because in polar coordinates, the limits here, well, for r, are going to be 0 to 2. And since we're looking at the whole circle, our theta will be 0 to 2 pi. Okay, so this double integral is going to be the integral from 0 to 2 pi, integral from 0 to 2 of negative 1 r dr d theta. And yes, anytime you have dA in polar coordinates, it's always r dr d theta. Okay. Next up, now we'll just integrate, right? We'll get the integral from 0 to 2 pi of, this will be negative 1/2 r squared from 0 to 2. And when we plug in the 2, that's a 4, so we end up with the integral from 0 to 2 pi of negative 2 d theta. Now, since we're just integrating a constant, it'll be negative 2 times 2 pi minus 0, or negative 4 pi. Well, I don't know about you, but this to me feels a lot nicer than what we just did. Maybe the same amount of work? I don't think so. I wrote a bit more here than probably was necessary. Okay? This is really the majority of our work here. Okay? So that's one way where Green's theorem really helps us out. Let me show you another example where Green's theorem really comes in handy. Okay, so let's evaluate the line integral of, and you can see this is kind of nasty, the natural log of x minus y cubed dx plus tan inverse y minus 3x squared. So, and where c is this square here. So it's a 2 by 2 square, kind of shifted away from the origin. Now, here is definitely an example where we will want to use Green's theorem, because if we don't, there are two well, maybe even more than that, but two big reasons why we would want to use Green's theorem here. One, this square, that's 4 different curves. Okay, we would have to take 4 different line integrals to do this. Okay, so each one of these paths here is given here, so we would actually have to set up a separate integral for each one of these. Then when we did that, we'd have a very nasty line integral each time. Also want to mention this is a circulation integral here, the f dx plus g dy. If it were a flux, we'd have a dy here and a minus dx here. Okay, just so we're clear that this is a circulation. And from here, if you were to actually set up all 4 of these integrals together, you get something that looked like this. I skipped a bunch of steps here, but you have to find an r prime for each of these, an f of r for each of these, take the dot product for each of these, set up your integral. Now we could combine this all into a single integral now because they all have the same 0 to 1 limits. But hopefully you can see that this is not going to be a very nice integral to deal with. So the long way here is nasty, right? So the line integral way is garbage, right? And oh God, imagine how terrible this would be if this was actually a circle, because we'd have cosines and sines inside of these functions, and it'd be even worse. So instead, let's use Green's theorem. Okay, using Green's theorem, remember the circulation f dot dr is going to be the double integral over big R of the, so if we're talking about the circulation here, it's going to be over the curl of f dA. Well, the curl of f, right, that's g sub x minus f sub y dA. Okay, well, if this is my little f and this is my little g, what's going to happen here, okay, just shifted this over, we'll get the integral over r of, well, g sub x, well, this is a y thing, so that whole thing disappears. So g sub x will just be negative 6x, and then minus f sub y, that will be minus a negative 3y squared dA. Okay, so we end up with, and here's the even better part, since this is a square, right, rectangular region, we can set this up in any order we want, and it's constant to constant. So we could do, say, x is on the outside, integral from 2 to 4, integral from 0 to 2, negative 6x plus 3y squared dy dx. Now this is going to be a much nicer problem to work with. Okay, so we'll have the integral from 2 to 4 of, now we're integrating with respect to y first, so it'll be negative 6xy plus y cubed. We're evaluating from 0 to 2. Okay, now thankfully the 0 will just cancel away, so really we're just plugging in the 2 to get a negative 12x plus 8 dx. Okay, and now it's turned into a Cal 1 problem, right? We'll get negative 6x squared plus 8x, and we will evaluate this from 4 to 2, right? So it'll be negative 6 times 4 squared plus 8 times 4. Okay, minus negative 6 times 2 squared plus 8 times 2. Okay, and so there we go. We've now taken a problem that would have been a major headache and turned it into something that's manageable, thanks to Green's theorem. All right, let's look at another example here. Let's find the flux and circulation of this vector field, f equals 2xy, comma x squared minus y squared, over the path c, which is given by this counterclockwise oriented curve here. So it's flat here, so that's y equals 0. It goes, say, from here to here, and then makes this parabola shape. Okay. Now I'm going to go ahead and say that I'm going to want to use Green's theorem here, specifically because one, this would take two integrals, but the other part is that for this particular vector field, I would need, or vector field, but part of the curve, I would need an oriented curve that does this. Okay, and that would end, right, that would end up being this particular curve here, this vector valued function 2 minus t replaced with x. That would let us go from t equals 0 to t equals 2. There are other ways we could do this, but orienting it that way, and then putting that in our f and taking the derivative, and I really don't want to do it this way. If we instead use Green's theorem, we can just take the double integral over this region, and our y limits are literally just going to be 0 to 2x minus x squared. We already have the limits the way we want. So by Green's theorem, okay, the flux is going to be the double integral over r, and flux matches divergence. So that would be the divergence of f dA. Well, the divergence of f, if we remember, is f sub x plus g sub y. So that will be the double integral over r of, well, f sub x will be 2y plus g sub y. That will be a minus, will be a minus 2y dA, and look at that, we get the double integral over 0, which is 0. So this vector field has 0 flux over C, and we were able to calculate that extremely quickly. I didn't even need to know what the limits of integration were because I know the divergence is 0, right? This is a source-free, so F is source-free, so has 0 flux everywhere, okay, or at least over closed curves, you know. Okay, let's find the circulation. So the circulation is going to be the double integral over r of the curl of f dA, which will be the double integral over r of g sub x minus f sub y dA. Let's see what we get now. So g sub x, that will be 2x, minus f sub y, which will also be 2x dA. And look at that, doesn't even matter what the limits are because we're taking the double integral over r of 0 again. So not only is f source-free, f is conservative. So has 0 circulation over C, and will have 0 circulation over any closed curve. So notice here that 0 divergence is kind of equivalent to being conservative. It's similar. 0 curl means you're conservative. 0 divergence means you're source-free. This is what we would call ideal flow, and I always think of this as we want, say, our bloodstream to be source-free and conservative, right? Because we don't want any sources or sinks in our bloodstream, right? We don't want any compressions that aren't there naturally. And we don't want any rotations in our bloodstream either. All right, so for our next example, let's calculate the flux and circulation of this vector field F equals 1 over 1 plus y squared, comma y over c. And where c is this triangle here with vertices 0, 0, 1, 0, 1, 1 oriented counterclockwise. Okay, so I'm definitely going to want to use Green's theorem here. And to do so, we need to find a way to come up with limits for this region R, right? Because for, say, the flux, by Green's theorem, that's going to be the double integral over R of the divergence of F. Okay, so the divergence of F, if we remember, is F sub x plus g sub y. And so F sub x, well, F is here, and this is just a constant with respect to x, so that will be 0. And then plus g sub y, that will be 1. So we're looking at the integral over r of 1 dA. So that shouldn't be too bad. We just need to find the limits. Now, we need to think about this in terms of, well, I guess we don't need to, but I'm planning to think about this in terms of bottom to top, right? So the bottom is definitely y equals 0, and the top, well, that is the line going from 0, 0 to 1, 1. Hopefully it's not too controversial to just say that that's y equals x. Okay, so our double integral is going to be 0 to 1, 0 to x, 1 dy dx. Okay, so when we integrate 1 with respect to y, well, now we'll have the integral from 0 to 1 of y, and applying the fundamental theorem of calculus here, we'll get the integral from 0 to 1 of x dx. So we get 1/2 x squared, which we'll evaluate from 0 to 1, and we'll just get 1/2. Okay, not too bad there. Right, so there's the flux integral. Now let's find the circulation. So the circulation, thankfully we can use these same limits that we just found, but the circulation is going to be the double integral over over R of the curl of f dA. Well, the curl is g sub x minus f sub y. And if we take a step back here to see what our capital F was, well, g sub x will be 0. And g sub y, well, that is going to be a much f sub y, it's going to be a little bit more complicated in this case. This isn't a constant anymore. Okay, so this derivative, if it helps, if you make it like this, right, 1 plus y squared all to the negative 1, or you could use the quotient rule, but I'm just going to say that is going to be, we'll bring the negative 1 out, so it would be plus 1 times 1 plus y squared to the negative 2 times the derivative of the inside, which is 2y, and then we'll have our dA here. Okay, so we're going to get, in our final step here, I'm going to set it up the same way. Hopefully it will still work, but we'll go from 0 to 1, 0 to x, of 2y over, actually, let me not do it that way. Let's say it's 2y times 1 plus y squared to the negative 2 dy dx. And the reason I'm writing it this way is because this is going to be a quick u substitution. Okay, so quick u substitution. because we'll leave the 2y, and we'll say that this is 1 plus y squared, the stuff, to the negative 1, all over negative 1, then times the derivative of the inside, which is the 2y. So this is what allows us to do our u substitution. Okay, so we will end up with, if I simplify this down, the integral from 0 to 1 of negative 1 over 1 plus y squared. We're going to evaluate that from 0 to x dx. Okay, so plugging in the x, we'll get negative 1 over 1 plus x squared. And plugging in 0, got to be careful here because we can actually plug in the 0 into our y and get something out, specifically be minus a negative 1, so plus 1 dx. All right, now hopefully we remember this integral here. Let me make this a little nicer. Let's say it's this. Okay, hopefully remember this integral as the tan inverse pattern, right? The integral of 1, of course, is just x. The integral of 1 over x squared is tangent inverse of x. Right, and then we'll just evaluate this from 0 to 1. So it'll be 1 minus tan inverse of 1, okay, minus 0 minus tan inverse of 0. Okay, so tan inverse of 1 is pi over 4, since that's the angle that makes tan equal to 1, and tan inverse of 0 is 0. So our final answer here is 1 minus pi over 4, and that is our circulation. Okay, so this is definitely a case where we would not want to do this one the long way. All right, so I think that pretty much covers it for what I wanted to show regarding Green's theorem. Should get you rolling on the homework, and I do definitely want to stress here how kind of breakthrough this Green's theorem thing is. If you imagine how, or think about how far we've come, right, in our calculus journey, right, from calculus 1 to calculus 3, we started with an extremely simple concept in calculus, specifically of the limits, right? The limit of f of x as x goes to a equals L, right? This idea of analyzing that what f gets close to as x gets close to a, right? This is a pretty simple idea, and from here we've built up, right, the derivative, right, the integral. We've created, we've looked at vector valued functions and their derivatives and integrals. We've looked at surfaces, right, and their derivatives, right, the partial derivatives. And we've looked at a lot of things, infinite series, all the way up to this idea that the circulation on the boundary, right, is completely dependent on the curl over the region, or that the flux on the boundary corresponds with the divergence in the region. Okay, this is an extremely powerful tool that we have built up from a fairly simple definition, fairly simple idea regarding the limits. Okay, I always like to kind of talk about this at the end of a semester of Calculus 3, because I know this class can be very overwhelming. It's very fast-paced, but think about how far you've come. This path is likely generations of mathematicians working on stuff. And yes, if you struggle to comprehend it and get your head around it in 3 semesters, that's not really that bad in the grand scheme of things, right? So I just wanted to leave you with that thought, hopefully make you feel a little better about how far you've come. And I will leave it there. I want to thank you all very much. Cheers.